Hi, today we will talk about a concept called the Poissons Ratio. So let's visualize this. If you have a Play-Doh and you're trying to cylinder it, you want to try to make a very thin cylinder shape. And so you roll it, you knead it, and so elongate it. So you will get extended. However, you realize it's going to be, for the cross section, it's getting thinner and thinner, right? And the cross section, the area, it's going to be getting smaller. So in the z-axis direction, it's going to be elongated. However, at cross section, the lateral direction, it contracts. So this is Poisson's ratio. It's talking about the ratio between the lateral over longitudinal. So it's using epsilon. Epsilon, we know it's a strain. So it's the strain in the lateral direction, the cross section, over the z-axis, the longitudinal direction. That's the Poisson's ratio. It looks like a V. And for each material, they're going to have their own specific ratio, Poisson's ratio. And that number can be also found at the inside of your back cover of your textbook, along with Young's modulus, elasticity modulus, or shear modulus. All those information is on there. Okay, so I actually invite you to pause the video to look at it to find out what is the A36 stainless steel. What's Poisson's ratio for that one? Okay. Well, I hope you pause and look for the value, and if you find it's 0.32, and that would be correct. So that's the value for V for A36 stainless steel. So knowing that, why is this information helpful? Because when you are studying a material, you might want to know how much is elongated at the z-axis direction, at the longitudinal direction. But you also want to know how much thinner it's get in the cross-section in terms of lateral direction. That's where this ratio comes to be really helpful. So knowing that, I invite you to look at this example over here. Not this one. So let's look at this one here. Okay, so this is a A36 stainless steel, has a dimension showing here, and we have an axial force 80 kilonewton applied by the bar, and so that's the longitudinal direction. And determine the change in its length, longitudinal, and the change in the dimension in the cross section. So the cross section is rectangular. You can see here, but it's gonna get smaller in both x direction, in the width, and the height in the y direction. So you want to see basically in those three dimensions, in the x and the y and the z, how much the change happens in the three direction. They said the material behaves elastically, which means it's in that elastic region. Okay, how do we solve this? We're going to review this really quick. Write down. So that's Poisson's ratio. It's negative epsilon, right? And it's which one to which one? Is lateral over longitudinal or longitudinal over lateral? Right? So make sure that's gonna be the right one. Lateral over longitudinal. Okay, so knowing that, and you find out Poisson's ratio for A36, this value is 0.32. Okay, now why, you might be wondering why there's a negative value to that. Okay, so think about it. Epsilon is the change in that direction over original length, right? So epsilon is delta L over original length. So if it's elongation for longitudinal, that epsilon gonna be positive value because it's elongated. However, in terms of lateral direction, longitudinal is going to be a positive value. However, for lateral, it's going to be negative because it's contracted if this is elongation. So knowing that, when you have lateral over longitudinal, you get a negative value. That's why there's a reason you have a negative in front of negative, so you get a positive value for Poissons ratio. Okay, now let's look at this problem. So knowing the force is 80 kilonewton, we can certainly go ahead and figure out what's the normal stress at z-axis direction. So that's going to be sigma is going to be over force over area, and our force is here P over cross-section area. And this force that's perpendicular to this rectangular surface is 80 kilonewton, and area is 50 times 100 millimeter square. Okay, so here I would like to change that 80 kilonewton to 80,000 Newton, because we do know Newton over millimeter square, that give us megapascal. We discussed that before. So then put that in there. So 80,000 divided by 5,000, and you would get 1.6, right? So we'll have 1.6 megapascal. Let's just double check. 80,000 divided by 5,000. We got 16 instead of 1.6. Okay, so that's 16 megapascal. Okay, so once we know that, we're going to figure out what's going to be the deformation, elongation in z-axis direction. Then we're going to using our Hooke's law. Hooke's law give us a relationship to connect the stress and the strain, right, in that elastic region, because this Young's modulus or elastic modulus, that's equal to stress sigma, normal stress over normal strain, epsilon. So look at the book, you will find for 836 the value for E, that is equal to 200 gigapascal. So make sure you are looking at that table. 200 gigapascal. And our normal stress is 16 megapascal, right? So 16 megapascal. Then with that, we can find how much normal strain would that be. So from here, we can calculate normal strain. That's going to be equal to our 16 megapascal over 200 gigapascal. Well, so here we can change giga to mega, so it will become 200,000 megapascal. All right. So when we do that, let's put it into calculator, see what we have. So 16 divided by 200. So I will have 0.08 times 10 to negative 3. So that means it's going to be 8 times 10 to negative 5. Okay, so that's our epsilon. And here I'm actually going to go back to give a subscript. This is an epsilon as a direction. At axis, at this axial direction, right? So that's what's the strain there. And be aware, this epsilon strain has no unit. We're talking about previously because strain is equal to the change, or you can use this delta or that delta, doesn't really matter, is equal to change delta in z direction over original length in this z direction. Original. Okay, so remember what our goal is to find out how much change happening in all x, y, z direction. Now we're about to find out one, which is z direction. Delta z, it's epsilon, the strain at z direction, times original length at z direction. Okay, so epsilon z is 8 times 10 to negative 5. And original length in the spar, for the spar, is 1.5 meter. So when we put all those in there, I will get 12 times 10 to negative 5 meter. Well, this is an awfully small value. Let's change that to, let's see, micrometer. So we know 1 meter is equal to 10 to the power of 6 micrometer, right? So knowing that, we're going to times 10 to the power of 6, then we get 120 micrometer. That tells us what's the change, how much elongated at z direction, 120 micrometer, very, very small amount, which is 0.12 millimeter. Okay, so 1 out of 3 accomplished. Then how about at cross section as x direction and y direction? We know they're gonna contract. We're gonna get smaller, but what's the actual change? That's when this new concept come along, this Poissons ratio. So now let's go ahead using that concept. V looks like negative epsilon. Remember, it's lateral over longitudinal. Again, look at the back of your book. You know for 836, V is equal to 0.32. Do we know lateral strain? We do not know how much contracted. However, we do know the longitudinal strain. That strain is not delta because that's actual change. Strain is the change over original, which you calculate in the step 2. That's your strain, how much in the z direction. So we're going to put over here, it's 8 times negative 5. That's your longitudinal or z direction. So knowing that, we can go ahead and calculate what is the lateral strain. So it's 0.32, put in my calculator, times 8. I got 2.56. Negative 2.56 times 10 to negative 5. Okay, so there is no unit for this because it's a strain. And knowing that, we can go back using the same concept we used for step 3 here to figure out what is actual change using the strain definition. So let's go ahead. The strain in lateral direction, which means applies for both x direction and y direction, right? Okay, because they're all gonna be having the same strain. So knowing that, let's look at the x direction first. So epsilon, let's use E, Hooke's law. E, elastic modulus, is going to be equal to stress over strain, right? So your stress, it's going to be that. Oh, what I'm doing. Don't worry about it. I get distracted. Okay, so in order to find the x direction, we're going to go use original definition for the strain. So epsilon x is going to be equal to the change in x direction delta, how much is contracted, over original length at L at x direction. Okay, you could say what's the width. right? So go ahead, we can put our value in there. Our epsilon x, which is lateral strain, it's negative 2.56 times 10 to negative 5. And what's x direction original length? Let's go back. X direction is here, and it is 100 millimeter. So let's put it in there, 100 millimeter. Then we can find how much change, what's the contraction at x direction. So delta x will be equal to negative 2.56 times 10 to negative 3 millimeter. Again, this is such a small amount. If we were to change that to micrometer, that will be negative 2.56 micrometer, because we know 1 millimeter is equal to 10 to the power 3 micrometer. So that's our x direction, and that negative is quite fitting, right? Because you know it's contraction. That's the final dimension is going to be smaller than the initial dimension. Therefore, you get change in negative. So then we got 2 out of 3 down. The last one is going to be our y direction. And you're the same the concept. So epsilon for the y direction, it's going to be the change in the y direction we're solving over original length in the y direction. So we know the strain. The strain we know it's going to be negative 2.56 times 10 to the power of negative 5. Then let's go back to look at our y direction original dimension. It is this value right here. That's 50 millimeter. Okay, so when we go ahead and calculate that, let's put in the calculator. So 2.56 times 50. I got 125. Negative 125 times 10 to negative 5 millimeter. Okay. Okay, so then if we're about to change that to micrometer, I feel this number is really huge. No, not really. Okay, so if we're going to change that to micrometer, we're going to times how much? We're going to times 10 to power of 3, right? 10 to the power of 3. So it's going to be 128 times 10 to negative 2 micrometer. Then that will give us negative 1.28 micrometer. That's our delta y, how much has been contracted at y direction. Okay, so let's wrap up this problem. We introduce this Poissons ratio and relate the longitudinal direction and lateral direction. And then using Hooke's law and using the strain original definition of changing length over original length, we can actually demonstrate we can get the change in all 3 dimensions. Alright, that's all for this video. I'll see you on the next one. Bye.